Hello, we are Team Dose presenting our medical monitor for home use. My name is Wesley Tiff.
My name's Clara Hall.
Drew Bell.
My name's Ethan Yu.
And I'm Quan Nguyen.
And Justin Mack will not be making it today. All right, as our introduction and, the usual, this is our new and improved quad chart. Our objective and concepts stay the same, where we plan to have started creating a medicine dispenser that regulates and administers medicine to patients who forget to self-medicate, including both liquid and pill medicine. We've begun doing so by creating a modified fridge that's been proven to have room to store both liquid and dry medicine, and the temperature regulates liquid medicine, also dispenses and reminds users to take their medicine while ensuring the safety of the user and the safety of said medicine. Thus far, our team has obtained a temperature-regulated refrigerator that stays between the temperatures 35 to 42 degrees Fahrenheit and properly stores medicine. It is designed, modeled, and created to hold both liquid and pill medicine dispensers, and that dispenses on command, while also allowing for customizability of the medicine being dispensed based on the user's needs, and performed analysis on fridge integration to allow for a grab tray to receive medicine, which we will talk about in the future presentation. When we look at our anticipated costs and funding request, our team has spent $140.03 so far, as we have obtained many free items and 3D printed a majority of our mechanical components, though we anticipate spending up to $464.73 more, including a $300 that's allocated to purchasing a new fridge for our final design. With that being said, our total estimated costs based off of our bill of materials is $697.15, though we will be requesting an additional $250 as we predict that we will have to update some designs or even upgrade some designs, and would like to account for the additional spending where needed.
The basic device functionality goes as follows. From our user interface, our user will program or select their medicinal needs, and that will tell our liquid dispenser or our pill dispenser to dispense whichever item that they've requested. It will then rotate to slot designated as slot 0, which will be at the bottom, and fall into the grab tray, being pushed out either by a rack-based system or rotated into a drop system. It will also contain extra storage for units of medicine that they may need, and will contain a blocked off electrical system, meaning that it will be housed separately on the opposite side of all our mechanical components.
In this slide, we will cover the objective that we're looking to achieve from this project. First, the system will safely guard the medicine inside, and only authorized personnel can access to it. Next, the system will allow users to select medicine through the user interface and dispense it. The device will be able to store both solid and liquid medicines. The system will have minimal external features such as power supplies, user interface, wires outside the fridge. The system will have multiple ways to get power so that it could continue to run in case of a power outage or disconnect from the socket. The device will be able to operate with minimal maintenance and repairs. And lastly, it should be easy to use.
All right, so starting off with our specifications, these are going to ensure the safety of our project and meeting those definitions that we just said. Starting off with our safety specifications, the first one that we have is about battery life. And the main point of this is to ensure that if the system is unplugged, the backup battery will be able to sustain power to all systems except for the cooling system in an event of unplugging or an intermittent power outage. And the main point of this is to ensure that if there was a short disconnect or something like that, then the scheduling system would not be reset. And that's the most important part of our project in delivering medicine on time and also consistently according to the prescriptions. That applies to everything except the cooling, like I said, and is not like impendent on that because of something that we'll talk about in the analysis, but as long as the door stays closed. Our next specification for the safety is notification, and that threshold is if one of our incidents happens that we've listed, it will notify the caregiver within 5 minutes of that via email. And ideally, we would want it to be within 1 minute, but that's our threshold there. And then the next two for medicine spillage and then the locked door access both have to do with our users not being able to access the medication unless if it's the designated time. So first of all, the medicine spillage SF03 specification is that if you were to move the fridge or pick it up and tip it over a certain amount of degrees, the pills would not fall out of their place. So that ensures the functionality of the device. So if it's moved at all, and that's going to happen during transport, that the functionality, it would still be able to dispense the medicine, and that will also help us do our other specifications as well. And then the locked door access is essentially to ensure that we're not allowing users to go inside of the fridge unless if it's the designated nurse or person that is servicing the device. And that is another test that we're going to be doing. And then finally, we have the electrical safety one, which is also involved with tampering. So basically saying that no one is able to tamper with the electrical controls in order to manipulate those to get medicine out of the device. And then that's also for safety as far as like electrical shock and all that. And then finally, we have our cleanability, which is providing a set of instructions for anyone who would be servicing the device in order to clean it, because we want to uphold the standards of medical quality, and then also that comes with sterility for the medicines. And then next we have our other specifications.
So these are our specifications for the parts of the project that we intend for a user to interact with, and the parts of the project that will interact with the user. The first are the light and sound alerts that will alert a user gently if it's time for them to take their medicine, and remind. Ideally, this will have lights and sound, but at minimum we are going to have lights flashing in order to alert someone. This will also occur anytime a significant event occurs that requires immediate attention. Our second specification is the display. We will have a day and time on screen of the next time the medicine will be dispensed, and as our absolute minimum. And ideally, we will have other notifications as well. Any information such as the medicine needs to be refilled soon, or that the temperature is irregular inside the fridge. And third, and this is an incredibly important part of our project, is the adjustable schedule. Ideally, so our project hinges on being able to have the user be able to determine when they want to have whichever medicines they place inside the machine to be dispensed at the proper time and day of their choosing. Now, at absolute minimum, we want them to be able to choose a time for them to have a medicine dispensed to them every day, but ideally we would like to have three different times, and choose which days they are supposed to be dispensed. We will be testing this one with trial runs of various times.
All right, so moving on to our design functional specifications. The goal of the medicine monitor overall is to be as slick and compact as possible while also being able to provide a variety of needs to the user. So starting off with our first design specification, the internal dispensers. So this specification states that the medicine monitor shall be able to fit all the liquid medicine dispensers specifically inside the fridge, but should fit all the liquid and dry medicine dispensers inside the fridge. So this is vital for the liquid medication that needs to be kept at a specific temperature, but if we can include the pill medicines as well, this would help for security and ensure that the patient does not have access to any medication, and that would make it significantly more difficult to break in. And this will be tested through 10 trials, and we'll be recording if the dispensers are able to fit while the lock is activated and if they dispense properly. The second design specification is cost, and this one talks about how the overall cost of the medicine monitor to produce should not exceed $1,350 and it should not exceed $750. Budgeting for the medicine monitor is important because we want to be sure to not exceed our budget, and we want to make this affordable for the consumer themselves. We'll monitor this specification by recording and budgeting what's been spent for the system and looking ahead to make sure planned parts that will be purchased in the future is accounted for and does not exceed the budget provided. Our third design specification is weight. So this one talks about how the medicine monitor shall not exceed 55 pounds and it should not exceed 80 pounds. This device we want to be light enough so that users who may travel frequently could bring it along if needed, and this can be achieved by considering the choices of materials and components of all the systems, and our final test will be weighing it with a scale. Our fourth design specification is storage. It talks about how the medicine monitor shall be able to provide storage for at least one non-loaded medication, and it should provide storage for at least 3 non-loaded medications, and that's 1 to 3 of each kind. So we want to have the ability to hold extra medicinal supplies. This would make it easier on a caregiver at any given time, and we want to be able to give it the ability to refrigerate these items. So a desired minimum square inch of internal storage would be about 3 inches in height, 5 inches in width, and 3 inches in depth. And we'll test this by using a measurement of the storage space that we create and how much storage can be verified via visual observation and measurements. Moving on to DF005, this one talks about the customization. So we want the dispensers to be able to hold pills and liquids with pre-filled vials of their choice. This customizability is non-negotiable. It will be doing this, and this means that it can be filled with medicine that's able to fit in each separate pill slot and liquid slot, and we'll verify this through observation as well as we're testing all of our trials in our other specifications. And then finally, the last design specification is the dimensions. And so this talks about the external size of the fridge remaining between the width of 20 inches and height of 20 inches and a width of 25 inches and height of 75 inches. So having a fridge that's small enough to fit in the patient's home is kind of what's important to us, as this is an at-home device. But the reason for having such a large range is because our team may decide to buy a new fridge in the future quarter for our final product, and this large range would give us more space and to allow for more customizability. And so we want the medicine monitor be able to be in the range between a small mini fridge and like a larger mini fridge. So that's why the range is much larger. And this will be tested by using a tape measure to measure the height and width of the medicine monitor's final product.
For our reliability specifications, we want our first one, suspension success, to be an 80% success rate, meaning that if there are any jams or unexpected errors that may occur, or we want 100% being a medical dispenser and a medical unit in general, so that our patient or users will get their medicine correctly and there will not be any account for liability or so forth. We are planning to test this through a trial run of 60 different runs and seeing where it lands and make adjustments from there. Our temperature, we are shooting for 35 to 42 degrees Fahrenheit. for our threshold and our objective 37 to 40. With all the electrical components that are being run in the machine, we will have to test the temperature in several different points, as well as seeing when the machine is running at a constant to see how much it warms up. We do not believe this is an issue, and we can still succeed this specification. For our suspension time, we are shooting for 3 minutes at a bare max, or at a maximum, and at a bare minimum 1 minute. The quicker that the patient is able to receive their pills, then the schedule can reset, as well as the dire need that they may need to take it on a very specific time period. This will be done through simple trial runs and see how long it takes using a stopwatch. For our fourth one is the grab tray. Since the pills and the liquids are dropping into the grab tray, we are making it at a 90 to 100% rate, with 95 to 100% rate as our absolute goal. This is accounting for any possible bouncing, it misses the drop, or some other unexpected means that we cannot predict. We are planning to do observation runs through 60 trials via opening the device and or putting a camera inside and just seeing the drop rate. Moving on to our next slide.
And now we have the electrical block diagram. I'm going to be going over just the general parts of it and how that connects with the rest of the device. So we've broken this down into the different subsystems, which are, first of all, on the left side, we have the dispensers in the bottom left for both liquid and solid medicine. And then those consist of the motors to control those. And then that's part of our also like temperature sensing area where we have the thermocouple. And then our other main parts are the grab tray, which has our infrared sensor, and that's for the person sensing when the medicine is taken. So that's an important part of our specifications. And then we also have the user interface underneath that, where we will have the ability to set the main schedule routine. And that also is part of the reminding system as far as the light and sound go. And then underneath that, we have the lock mechanism, which involves the open door sensor, and that's part of our safety specifications as well. Just keeping tabs on when the door is open or if it opens when it's not supposed to be. And then also, so for our basic like wiring part, I'm going to show this in the wiring diagram in a minute. But we have, first of all, since we're using a fridge that is like off the shelf parts, this whole circuit is powered through the wall power. So as you can see in the top there, we have the power supply, and then we're actually going to be branching this out from that to supply the other systems, including the dispensers and also our backup battery power, which you can see on the right here or in the top center. So that will be connected via a charge regulator to the converter once it's in DC, and then the rest of this whole system is run by DC power. And then finally, our microcontroller, which you can see in blue, all of those is the same one. That is powered by 3.7 volts, so we need a step-down converter for that, and that goes from the 12 volts to the 3.7. And then next we have our schematics, which takes a deeper dive into just kind of the same things that I was just showing you. So on the right, we have the light and the sound circuits, and the light one's pretty simple. It's just like emitting light, and then same for the speaker, it takes the signal. And then in green, you can see the three main sensors that we have. The most basic one is the door open sensor, which is basically just a switch that detects when the door is open or shut. And then we also have our infrared sensor for the grab tray, and then the thermocouple, which is our temperature sensor to make sure that the device is at the correct temperature. And that's also part of our alertion system that will tell the caretaker whether the temperature is out of range. And then we also, on the top, this is part of the charge circuit on the top left. for the 12-volt battery for our backup battery system. And that, again, that only powers the DC power, not the AC, as our design goes. And then right next to that, you can see the converter, and that is for the Arduino power, and that's actually supposed to say 3.7 volts, but you can, in the diagram, it's 12 volts to 3.7. And then our next schematics are all the same. These are just the motor controllers. You can go on. And they're all the exact same thing for those. Next, for our wiring diagram, this is just a bigger picture for putting that all together and seeing how everything connects. So on the top right, you can see the motors for the dispensing systems. Those are all numbered according to our other block diagrams as well. So the codes all match up there, and all of those have digital I/O ports that go into the center, which is our main microcontroller, and that actually is just blown up so you can see some of the ports. But we will be adding more I/O than we actually have available right now. So we're looking into a way right now to see if we can do an extension of the MKR 1000, which is our current microcontroller, or if we need to interface it with a separate Arduino Uno. But as of right now, this is our current wiring diagram with everything. So that includes, on the right side, on the bottom left, we have our IR sensor, which is for the grab tray, and then the door sensor and the thermocouple. And then on the left, on the bottom, you can see the charge circuit and where that plugs into the main fridge area, and then how that connects, and then the light's just over there on the side by itself. But yeah, that sums up most of the electrical parts, and if you could just follow along, that would be how you would wire it together. So yeah, now we're going to go on to the mechanical side.
All right, for our mechanical block diagram, we have our cooling system, which will contain our motor holders connected to our actual motor, which will then be connected to our rod-based system, to our liquid system, which will then drop out our syringes. That is all held in place by 3 to 4 10mm screws. We will also have our pill system inside the refrigerated system, which will also be held by its own housing. It will have a turntable located on top with the motor connected to it and the pills inside. Again, it will also be connected with 3 to 4 10mm screws that can hold it. We do plan on 2 of each, but as our specs do say, we have 1 liquid and 2 pill. For our electrical components in the bottom left, it will have its own separate housing, and it will also be located within the fridge, opposite side of our mechanical components. It will be contained with 4 25mm screws, and that will have an extra spot on the side in case we do not have enough room. We do have extra room on different parts of the fridge for stuff that is unplanned for. And finally, for our FD portion, we have the mechanical lock that is located outside of the fridge, which it will be at the moment a pad lock based system that we can lock up and can be unlocked via key. It will have the grab tray located inside, which will have a sensor that tells when the door is unlocked and unlocked, or locked and unlocked is what I meant to say. And the motors that are controlling that'll move it back and forth so that the user is able to grab it. Other than that, that sums up the mechanical block diagram, and moving on to the next portion.
This is the software logic flow chart that will detail the most important functions of the software run by the MKR 1000 during regular runtime. It will start by always displaying the next time for a medicine dispensation, and usually this will remain unchanged. Now, only when it's time to dispense will it move into the medicine dispensation protocol, in which it will flash and send a buzzer to alert the user that their medicine is there. and then it will repeat this. It will repeat this if the medicine is not taken from the grab tray up to 3 times, upon which the system will send an email to the caretaker and record the event. It will also send an email and record the event in case of any other kind of emergency or failure, such as temperature issues or storage breaches. Next slide, please.
So these are the analysis that we did for each system in 4 quarters. For the pill dispenser, we calculate the decrease to turn for each comment and made a CAD model for it. We also did the same for the liquid dispensers. For the motors, we analyzed different stepper motors and choose the most efficient one based on the amount of power consumed and the torque. Then we calculate the required torque to spin the dispensers. For the grab tray, we create sketches and came up with some basic ideas for it. For the sensors and emitters, we assess the placement for the electrical components inside the fridge and design amplifiers. For electronics, we design a basic circuit that needs to power all the system and components. We also analyze the operating temperatures of the microcontrollers and motors and other electrical components. We also research the microcontroller Wi-Fi seal compatibility. Next slide.
All right, for quarter 2, we have redesigned our liquid dispenser. Being that it was slipping on the first quarter, we have added a rod-based system to fix it, and we are awaiting testing. Our motors, we have ordered new motors. The original ones didn't quite work. The basic gist that was the voltage was too high, and more will be detailed onto the next slide. Our grab tray has been finalized. We have selected our dimensions, and we have our 3D model ready, and we are planning to work into the shop as of this week. For our fridge door lock, as stated before, we are going with mechanical design rather than an electrical. It will be placed on the outside and use a padlock-based system as of right now. Our fridge door is along with our grab tray again. We are going to cut into it. Sensors and emitters will be located on the inside. We have selected them, and we are needing of wiring and testing to make sure that it is going smoothly. All electronics, again, will be housed inside it with its own separate housing, and we do not believe there's an issue there as it is complete. Our electrics layout, we have our design. We just need to make sure that everything fits nice and snug. The housing units and our 3D CAD file does support this, but we may have to add extra features or extra components if necessary. As stated with our microcontroller, we may have to have a second one just in case, but we are still testing to make sure that is not an issue. And finally, for our user interface, we have not programmed that yet, but we need to configure the LCD screen along with the buttons that need to either be 3D printed or ordered and put into the front panel of the door so that the user can use it. And moving on to our next slide.
Okay, so talking a little bit more about the motors. In quarter 1, we analyzed a NEMA 2-phase stepper motor, which were the motors we found in SPU's labs. These motors, unfortunately, were not compatible with the system as they required too much power and the microcontroller could not keep up. We didn't account for the compatibility with the microcontroller when we were testing last quarter, so we reordered more motors over winter break that are similar in size and shape. But they require 3.4 volts compared to 12 volts and less torque. So these motors are the NEMA 17, which is data sheet we have in the appendix of our engineering analysis. And this motor was run through the same code created in quarter 1. So based on the figure 1 results on the screen, the new NEMA 17 motors need less power to run than the original motors. And therefore, these motors, we believe, will still produce enough power and efficiency to be compatible with the microcontroller, but also be efficient enough to run both the liquid and pill dispensers. And then on the next slide, for the grab tray, and a little bit more specific, in Q1, we did grasp a really basic concept of what we wanted to do for the grab tray integration. Within the first few weeks of Q2, we finalized this design, produced CAD files for the grab tray and the sliding side mounts, and gave it exact dimensions, materials, and a complete manufacturing plan that we will be working in the shop on Wednesday. So the grab tray will be 12 inches in width, 3 inches in depth, and will sit at the bottom of the fridge. It will be made out of polystyrene and insulated with Loctite gaps and cracks insulating foam, along with a silicone clear caulk to ensure that no cool air leaks out when it's opening and closing. The grab tray will also be mounted using stainless steel sliding side mounts that will be attached to the fridge door. And this is kind of a photo of the concept of the grab tray, though it will not be 3D printed.
So we did some modification to the fridge door. We removed the inside plastic holder, which was unnecessary to our project as it takes too much space and couldn't hold any of our system. Because the holder is also act as an insulator, we will re-insulate the fridge door later. So here are some of the ideas for the door lock that we came up with. The first idea is the exterior chain and lock, which will have a chain to secure the lock, removable lock, and the screw to attach the lock to the fridge door. Next is the padlock system, which requires hinges and a lock and a screw, and it will also be to the fridge door. Next is a deadbolt system, which requires deadbolt lock, screws, and the ability to add electrical components. And to the right here is the SolidWorks model of the padlock system. We won't be making this system, but the SolidWorks model was great to test out the concept. Next slide, please.
All right, so for our engineering electrical analysis, I did two main parts of this, and the first one is the power being supplied to unit, and then the second one was the components that we would need as far as like everything to control the device and also meet our specifications. So like Wes was saying, we have a little bit more pieces that might be added, but as far as the current design goes, we have everything that we need to meet our threshold specification. So the only reason why we would add any more motors is to add another liquid dispenser. So the main point of this analysis was to just make sure that all of the components would fit inside of the fridge. And that just demonstrates the ability to meet our specification for the user not to be able to tamper with that. And then the other part was just the charging circuit, making sure that the correct amount of voltage would be supplied to the battery and that it would be able to run, which we're going to have to do more analysis as far as testing that to see how long the battery backup system can last. But as far as right now, we just have the design for that. So we're going to have to run testing. And then next.
So this is our engineering analysis for the user interface and microcontroller. We are planning to use an LCD screen and push buttons for programming the schedule that will be used for the rest of the week. The default state will show the next dispensation time, and if there are any irregularities in the system, that will ideally display on screen as well as the other alarms, the light and sound, the LED and buzzer systems. The MKR 1000 will connect to the internet and send an email to the caretaker when it is necessary, such as during those aforementioned emergencies, or when a user does not take the medicine for an extended period of time.
Are there any questions?
And that wraps up our presentation.
All right, well,
Thank
thank you.
See you tomorrow.